thanking DBIA for having us here today to talk about this project and for the project of the year award. It was unexpected, but very much appreciated. As this was mentioned, my name is Jared, but we're at the Proper Murphy Utility in St. Louis. And with me today is Josh Cole with Food Brothers Construction. And we're here to talk to you about the MacArthur Bridge, the West Approach Stand and Posted on Broadway Avenue. Next slide. Just a quick overview of what we're going to talk about today. I'll get to the boring parts. I'll talk about the history and description of the bridge, the description of the project, some of the finer points of the design build contract, some of the unique parts of the bridge design, and then Josh will show you all the full pictures of the bridge construction and the repair. Next slide, please. This is just an overview of the MacArthur Bridge complex. If you're not familiar with it, it's south of the Poplar Street Bridge in downtown St. Louis. The red star is where our project was actually located. As we mentioned, the MacArthur Bridge is a very long railroad bridge. I think it's got 3.5 miles of elevated structures between the east and west coast. The main spans over the river, the Mississippi River, and the north and south roads. But you see the little apartments logo there. That's supposed to be where we stay. Very big bridge, and you this is small part of it. Next slide. This is an old photo of the bridge. Our project is that truss that you see in the foreground there. The original MacArthur Bridge has 2 lanes of rail traffic over the river and had an upper roadway back that used to run across the river as well. The bridge was built to break the monopoly of the Terminal Railroad in St. Louis. They owned the other 2 railroad crossings, the Merchants Bridge and the East Bridge. The local merchants weren't happy that they couldn't get the traffic across the river without being told from the Terminal Railroad. So the city of St. Louis opted to build the MacArthur Bridge, which was originally called the Municipal Bridge, crossing the river. And like I said, you can see our project is in the foreground. It's the 2 trusses, the railroad truss and the highway truss. Next slide, please. So a further description of the bridge. This is a view looking south. This is the railroad truss that's spanned the Broadway. This is a little bit of a unique configuration. It had to do with a lot with the way the businesses were located around the bridge where it was built. There were a lot of old warehouses and business districts were situated on the bridge. You see the gas station in the foreground. You see the price of gas. You kind of track that through our project. You see it go up over time. But this is the railroad truss. Carries the eastbound and westbound traffic. Next slide. This is the abandoned highway truss. This is the one you saw in the old photo. This was a particular concern to us during this project with the deteriorated conditions. Concrete had been removed off the bridge a long time ago. This highway truss will supported the old highway traffic going across the river and the eastbound traffic for the railroads. This is the view up on the deck on the right hand or on the left hand side there. You can see the abandoned highway truss. This is just pictured here in demo. You see the track that's running in between the 2 trusses. That's kind of a unique configuration. I haven't seen this anywhere else. On travels around the country, but that track is supported both from the highway truss on the left-hand side and the rail truss on the right-hand side, and then the other rail line runs on that railroad truss that's on the opposite side of the picture. Just another view of it. You can see how the 2 tracks are configured going through there. This is going to play. Josh was talking about our change on the bridge. Next slide. So a little bit of history of the bridge. So it was built in 1909, 1917. It opened vehicle traffic with the municipal bridge with the free bridge across the river. 1929, the bridge was actually completed. All the approaches were completed and it was open to local rail traffic. But it didn't really see real rail traffic until about 1940. In 1942, it was renamed MacArthur Bridge after Douglas MacArthur. In 1981, the road deck deteriorated. The road deck was closed. Eventually, Terminal Railroad removed that from the bridge. In 1989, Terminal Railroad took ownership of the bridge. Like I said, they used to own the other two bridges across the river. They still own Merchants Bridge. They own the East Bridge, the first bridge across the river in St. Louis. It limited rail traffic through the area because of the tunnels off the west end of the East Bridge. So Terminal Railroad and the City of St. Louis swapped bridges. Terminal Railroad took on the MacArthur Bridge. The City of St. Louis took on the East Bridge, and they were able to convert that. That was their contribution to Metrolink in St. Louis. They gave by state the East Bridge to use for Metrolink. Next slide. I'm happy to get out the slides here so I can read all this to you. This history. But the designer of the bridge was Alfred Pentecost Paul. And he was somewhat of a famous bridge engineer at the time. Kind of known around New York. His most famous project was the base for the Statue of Liberty. The builder of the bridge was American Bridge, the original American Bridge that this is one of the bridges. So a little description of the project. As I showed you, we have the two trusses across Broadway. We replaced that single-span truss with a three-span curved bridge. We demolished the abandoned roadway bridges in the area and built a small retaining wall around it. We had a student's buildings for the school. Next slide. So Terminal Railroad set out some goals for the project. Those goals were they wanted to replace the aging structure. They were looking to increase the effective car width of the travel bridge from 13 foot 4 inches to 15 foot. And this is related to item C here, allowing at least 20 dimensional loads per year to travel the most efficient route through the country. This bridge carries Union Pacific's main lines to the center of the country from east to west, across the Mississippi River. The next closest crossing is Cape Girardeau or Clinton, Iowa. So it's a pretty good reroute. They can't run this bridge. And when we talk about dimensional loads, we're talking about high and wide loads. These are the equivalent of a high or a wide load on the highway, a permanent load on the highway. And what limited traffic on the MacArthur Bridge is a curve that runs up to the trusses or ran up to the trusses on the railroad bridge. And if you're familiar with how a railroad car traverses a curve, the wheels may stay on the track. They turn the load swings wide and it's articulated on the trucks on the cars, so it swings into the curve and out of the curve and going around. So because that truss is stuck up above the tracks, and because that curve is running at the end of it, we have to be careful with the loads when we're across the bridge, constructing the bridge. So when they couldn't run the bridge, run the cars that way, they had to reroute them to either Cape Girardeau, Memphis, or Congress. So this was a way to pass more loads over the most efficient route. Another goal was to minimize the impact of rail traffic for the Terminal Railroad, the Union Pacific Railroad. If you're ever working on railroads, that's the most important part of their operations. They don't shut down for anything, minimize the amount of time they're out of service, because when they do, it backs up cars for miles and has ripple effects throughout the system. So I think we were great on this the least amount of impact of rail traffic. They also wanted to change the span from an open deck to a ballast deck. If you're not familiar with an open deck or ballast deck configuration, an open deck is one where if you're standing on the deck, you can see through the tires to the ground. That's what they had. As you can imagine, as trains go over, they may drop things off, whether it be ballast rock or coal or things may fall through. And they didn't want anything falling on the Broadway afterwards. So the ballast deck is much heavier. That was the challenges for our design. So that was one of the things we were great on. And we also had to maintain vertical clearance over Broadway Avenue. The City of St. Louis required us to maintain this 29 feet, and that was due to the Mardi Gras where it was. Had to keep the vertical clearance high and pass those. Next slide. The funding for the project came from a grant, prison grant from the federal government, $7.1 million, and the Terminal Railroad kicked in another $7.1 million. Next slide. As far as coordination with the terminal railroad, the train or the bridge passes about 4, I think it's 4 or 6 tracks. But there's a station right off the end of the bridge, and that's the way they go across the river, head towards Chicago, or head south. They have normal rail traffic, Union Pacific Railroad. The Southern Railroad is right off the east approach of the bridge, where they run their daily traffic. And there's also reroutes from the merchant terminal railroads to the other bridge. On the next slide, you'll see that terminal railroad had another project going on at the same time as this, and that was to replace the main span trusses that we used on the merchant's bridge. So when they can't run the merchant's bridge, they have to run the Carthage bridge. So that increases the road traffic on our project. Next slide, please. We also have coordinated with the city of St. Louis. We did put a foundation underneath Broadway. It required a plan review with the city. It required us to maintain traffic on Broadway Avenue for cardinal games or cardinal game-like events. There was a lot of traffic, as you can imagine. It was 3-4 blocks away from Busch Stadium, so that's one of the main avenues to get people away from and to the stadium. So we weren't allowed to close down the roadway when there was a game going on. What we ended up doing was scheduling our outage to replace the bridge during the all-star break when the Cardinals were out of town for an extended period of time. Next slide, please. As you mentioned, the project team was Goodman Brothers, the prime contractor, and Crawford Working Utilities and Design. Transsystems was also on our team, and they were the designer of the main span superstructure. Next slide. Just a little overview of our contract. It's kind of what I'm here for today, design build aspects of it. Design build fit this project really well. It's kind of a unique situation. The framing of the structure allowed for a lot of innovation in the way we chose to do our design. We chose to do our change out. So the design build allowed us to work with the contractor to come up with some unique approaches that we designed and change out this bridge. And it allowed us to find ways to minimize the interruptions to terminals traffic. We had a design bid build. We may have come up with some design that didn't fit the contractor so well and set it. So this turned out to be a really great way to utilize design build. It was a fixed price contract with liquidated damages of $15,000 per hour for double track outages in excess of the proposed outage and proposal. Terminal in the RFP allowed for 96 hours available for double track outages. And we have all the single track outages that we wanted, but double track outages were only 96 hours. We proposed 48 hours. There was some additional work on the project through change orders, and we were able to be efficient in the work we did, saving some money, so we took that extra money and were able to demolish some of the old highway structure, kind of improve the area and neighborhood around there, and did some existing road repairs as well. Next slide, please. I think there were several keys to success on this design build project. One was understanding our client. Both worked with terminal railroad extensively in the past. I used to work there as a manager. Pretty well manager of the Charlie's Bridge. I had an understanding of them. Crawford Working Utilities worked with them. Good with as well. So we had a good understanding of our clients' needs. Also unique to this project because I worked with terminal railroad. Not only was I allowed people to be designers, but Goodman Brothers had to go out and be the quality control manager and safety manager on the project. So Josh and I were working together side by side. Something came up during the project, there was a design change or something wasn't working quite right. We were able to make changes on the fly pretty quickly without a lot of back and forth. We were also able to come up with an innovative foundation for this bridge that saved a lot of money and was able to install this constrained environment. Next slide, please. So in October of 2020, the RFP was issued. In January 2021, the selected project team was selected. In September, the design was farmed along, construction began on the piers. And in July 2022, like I said, during the all-star break, we replaced the span. In project was fully completed in March of 2023. Next slide, please. So getting into some of the design aspects, if you're not familiar with St. Louis, there used to be a creek that ran through downtown called Mill Creek. And there's a Mill Creek Valley which showed a pond, and that's what you see there, kind of overlay when you see where the pond used to be. There's old pictures of people riding the boats around downtown St. Louis on the pond. But the star there is where our project is located. Because of the creek and pond that was there and the runoff, we had alluvial soils with soft and medium clays. Also unique was the depth of bedrock. If you can imagine, from one side of the project to the other, as we were doing our geotech investigations, 100 feet, our span is 19 feet long. So say 100 feet, there was a difference in bedrock, our distance to bedrock from 54 feet to 74 feet. So there's quite a variation from one side of the other to the other. Next slide, please. So typically on a project like this with constrained overhead, or with vertical overhead, clearance issues, we look at the foundation of micropiles. The reason being, they can be installed easily, like I said, low overhead. There's small diameter pipe. There's minimal ground vibration when you do that. It's you install it up against the existing bridge without having to worry about damaging the bridge or affecting it. They have high tensile capacity installed in the rock, and they have a high compression capacity. Coogan came to us during the RFP phase and said, "What do you think about using helical piles?" We had never used helical piles, and like any good engineer, he said, "We got to investigate this." We don't know, but we sure look into it. Helical piles have the same advantage of low overhead installation. It's the same small diameter pipe that you would use for a micropile casing. There's no ground vibration with helical pile installation. They have a very high compression capacity. They can be installed backwards, which is great for the longitudinal forces we have to deal with. And for this project, it was a much lower cost. It's a much smaller crew, much quicker installation. I think of this project, we estimate to save about $500,000. Next slide, please. So as part of our investigation, we started looking into these helical piles. We found out, of course, the helical pile contractors, subcontractors said, "Oh yeah, we can use these for railroad bridges. Go ahead." They've been used all over. We found out that they indeed have not been used on railroad bridges before. So Terminal Railroad allowed us to go forward with this as long as we did test piles, intensive tests, compression tests, and the BNSF and Union Pacific and Amtrak, all of the users of the bridge, all approved the use of the helical piles in these tests. Next slide, please. So if you've seen helical piles before, you've probably seen one of these commercials where they talk about jacking and basically the foundation. It's the same sort of principle. We didn't use it quite this way, but this is how helical pile would work. You screw these things into the ground, and the helix on the end of the pile provides your resistance both in tension and compression. In our case, this was just a method to get a pile down to bedrock. We screwed these piles all the way in until they were sitting on bedrock, and that was our bearing for our compression. Next slide, please. This was just a slide that shows our test rig that we used. We had helical piles on both sides. We did a couple of tension tests, a compression test. Our helical pile subcontractors said, "Oh yeah, we can get 200 kips of tensile capacity out of these piles," and they failed miserably. We tried to put things right back out of the ground. Maybe I'm exaggerating, but we got about 40 kips. I need to change this slide. We got 200 kips of tension. But when we did compression tests, they performed great. We got like 700 kips of compression. I think we could have ripped the testing rig out of the ground, pushing on these piles. So what we ended up doing was going back to the drawing board and revising our design to only use the piles with compression, and just ended up making the footing a little bit bigger. And I think Josh is going to take over now and show you some of the cool pictures of construction.
Okay. Here. Jared was saying, here's when we started, this is actually when we started for the tension test, and compression test. So it was a Komatsu 490 that screwed the piles in the ground. You can see the install head on the tip of the boom for the machine. They had a gauge or some kind of computer inside the actual cab that they could see as they were screwing them down what capacity they were getting on the pile. And that's kind of what they knew where they needed to be. But like Jared said, we also had to go all the way to bedrock. So it didn't really matter if everything got screwed all the way down. They came in 20-foot sections. They were pinned together. There was concern about the slop and the play on the pins when we did do the tension test. But like Jared said, that didn't matter. I mean, we literally pulled the pile right out of the ground. They utterly dealt with it really bad. But we got that worked out. And then once they were installed, everything got grouted solid. So a solid pile. Next slide. This is the foundations on the west side of Broadway. And like Jared was saying, the bedrock was all over the place. And you can see here that the piles are actually not, we expect them to be all pretty up the same elevation when we finished putting them in, and they were not. So there was concern between Jared and myself if we were all the way to bedrock or how we were bearing. But everything worked out in the end. From here, we cut them off, had to put, we didn't have to put the pop caps on. We cut them off, grabbed them solid, and moved forward. Next slide. So this is on the east side of Broadway. And you can see right next to the files, there's a pancake foundation. That's the old foundation for the bridge. And we had to miss that. And Almeida, our piling sub, they were actually able to model how the piles went down. Underneath those pancakes, there was also old or concrete piles from the back when it had been constructed before. So we had to make sure we missed those and stayed out of that. And again, vibrations were a concern. That just shows you how close we were to the existing foundation, where the concrete barriers are is right on the edge of Broadway. Next slide. So here's the piers or the columns going up. You can see how tight we were up underneath the bridge. That, for reference, that's a little 20-meter pump truck. I mean, it was, when we got before the vents up at the very top, the little caps, we had to just take everything off the pump truck. We were just pouring out the ductile. We had to go in between the steel on the existing bridge. Like I said, just extremely tight conditions. This is looking east, so that's the east side of the bridge. And BP's on the other side. Just kind of showing how tight it was. Next slide. So once construction was completed, the new foundations, they got time to do the change out. Here we are loading the first set of girders. I don't know if this was the east or the westbound, but anyway, you can see that the train was running as we were trying to load these things. And what we did is we brought the trucks in, picked the girders off. We set them actually on storage containers that were level, and it allowed us to basically assemble the bridge off-site or out of place, and then make our storage case. Next slide. So this is on the west side of Broadway, how we had to connect. Up at the top, the two existing cross members, cross girders, we had to tie into those. Some strengthening had to be done. And we actually ended up replacing the top angle piece. Kind of in design, we thought we didn't have to, but as we got going on, we realized that top angle was eating up a lot more than it should have been, and ended up having to replace that as well too. But the existing bridge sat right on top of those, so we were able to remove that, and then the new jump stands sat on top of the cross girders. Next slide. On the east side, kind of similar. It's hard to see in this picture, but anyway, on the left side of the picture, that jump span actually got removed back to that. If you can kind of see there's another cross member here, the cross curve that it's sitting on. That's after the new jump span has been set on the side. Next slide.
So as part of the change out, we had to do a lot of preparation, a lot of planning. As you can imagine, $15,000 an hour in liquidated damages, hanging over our heads, we had to be prepared for this whole change out, make sure that it's smooth and got into it. Part of this is the change out, I just see in those later slides, we use an SMT, a self-developable transporter trailer to move these trusses out of the way. We have two of them and move them for subcontractor to do that. Great guys, as you can imagine, they want to know the dead loads of these spans that they're taking out. As I mentioned, you have a railroad truss that you have the railroad truss and the highway truss, and there's 4 different truss lines. One truss line was carrying half of the railroad track, one was carrying a full railroad track, one was carrying half the railroad track, half the roadway deck, and one was carrying half of the roadway section. It's kind of unique in this situation because every one of those truss lines is different weight and size and road requirements. So as part of that, we have to find the centroid, the center of gravity of these trusses, both east, west, north, south, and vertically. So when we would use our calculus to make sure that they don't tip over. We also had to analyze the existing deteriorated highway truss for strength. And we picked it in a different way. It's been sitting on bearing. Fall down as we're picking off the supports. We needed to size the girders to support that eastbound track. So the first thing to come out was the highway truss, and when we removed the highway truss, and the eastbound track is no longer supported. So the beams for the eastbound track, which is the beams on the stone years, support that eastbound track and get the size. It's kind of hard to maybe notice in some of the other pictures, but it was a very tight site. BP on one corner, we have a substation directly across from that on the other corner, and we have Taco Bell on the other side. It was very constrained, we wouldn't hold out, we wouldn't move. So what we ended up doing is Josh did a slide with a LiDAR drone picture of the site, and we modeled the site for equipment where it was. We had set it where we were going to move the existing trusses, we took them down, how we were going to put them out of the way, and we used this in place. And we had to estimate the time for each one of the because we're on the clock and we go through the damages. So there's a lot of planning that went into it, and lots of planning and lots of meetings to make sure that we're ready for this. So there really does a lot of change out. It's not so much particularly complicated.
Like Jared said, the time had to be estimated for each piece, and terminal actually came to us and they wanted an hour-by-hour schedule for the entire changeout. Initially, at the proposal time, I think we were proposed doing this in 24-hour segments. I think it was 5 days. It was a 5 or 6 day turnaround, working around the clock. They were concerned about working at night. If you've ever been downtown, it's not exactly the safest spot, so they didn't want us working at night. And again, had to do an hourly schedule to make sure we were meeting that. And with everything being so tight, I think in the next slide, yeah, so you can see the site as far as where Cameron's at. Like I said, Taco Bell, BP. There just wasn't much room to try and get everything moved around that we needed to. Just to the left of the green, you can see the new spans actually sitting on the containers, ready to go in place. That was our laydown yard, and that's all we had to get everything kind of. When we moved in, we were able to close 6th Street, which is the street just to the left of the new spans, and then we were able to take that, our laydown yard, and when we did the change out, we shut Broadway down to Gratiot, which is just at the top of the screen, all the way down to Shoto. That was the only space we had. So we had to make sure that we were moving the bridge set, the old bridge sections out, the new bridge sections in, and we had space in order to make sure we could set them down, how long it was going to take to carry them apart, and things of that nature. Because we moved it and not have, they only brought in one section, two of the large mats, that supported everything, but we had to make sure certain things were done before we could reuse those. Like Kara said, the old highway truss was supported the existing railroad bridge into the railroad. So we had to support the eastbound track structure first. This is when they were bringing in a couple of the 90-foot beams that they had. We set these up on our existing, our new piers before to support that truss, or support that track section. We got everything pressed into place, and we got that supported. That's all. Here, the SPMT is in the background. It's got a set of I think those are 80-foot mats. That is going to support the highway truss. In the foreground, you can see the beam running across our new piers. That is now supporting the eastbound track, ready to cut everything. Here we are, we moved the SPMT into place. We've got up underneath the highway truss. Everything is supported at this time, and we're ready to start that stuff. Got everything free. Next slide. So what we ended up doing to get rid of the highway truss, we basically cut the end boards off, and we were able to just kind of create a rectangular box and lower that straight down. Next slide. Here we are, we've got the ends cut off of it. And then what we did from here is we just lowered the structure straight down, turned it, and then walked it south of Broadway, get it out of the way. We then set it on some cribbing, got the transports out of the way, and then produced our demo stuff there and started tearing it apart. Like I mentioned earlier, we had to have the mats back and get reset up to use those again for the railroad truss. So again, we had to make sure as we were setting the new span in that we had time to tear this whole piece apart and just make sure that okay, so here, this lower, get ready to walk it to the south. After the old span was out, so that was the roadway coming out. Once the roadway was out, we had to pull the eastbound track section out, and then from there we were able to put the new eastbound span in. And so the new spans, like you saw earlier, were sitting on containers. We had to pick those up, walk them into the site, and then lift them up and then set them on the new piers. Next slide. So after the eastbound span was in service, and jump spans were set, everything like that. And the jump spans are what connected the piers to the existing points of the bridge. That's what made those connections. So once everything was in place and eastbound was up running again, we then took the westbound truss out. We did the same thing here, where we cut the end boards off. But instead of, we couldn't lower this one straight down because as you can kind of see, the track section still extended beyond the piers. So we had to walk this one directly to the north a little bit, then we were able to spin it and lower it and continue on the way. Next slide. One thing that we did not think about during the changeout in any of our planning was a gas station. And Larry Goodwin, who's the owner, came out when we were in the middle of this, 1 or 2 days into it, and said, "What are we going to do about the gas station?" Jared and I kind of looked at each other like, "Oh shit." Nobody, I mean, if the video plays at the end, you can kind of see all the lancing that happens and all the cutting and just all the burning that had to happen in order to get the old spans out. Through sparks everywhere, and again, we weren't really thinking about the gas station. Kind of where the fire department's at, where the storage tanks are at in the ground. And so anyway, yeah, if we would have thrown sparks over there, it would have bad news. We would have made the St. Louis news for something we didn't really want to. So we went up and talked to the owners, ended up shutting down half the BP for a day, and we demoed the old piece out, and then we got right back to the service. Had the fire department on site, I think, for nearly the entire time we were doing that, so that was kind of a nice piece of once that westbound was out, like you can see, we spun it, and then we're walking it north on Broadway to get it out of the way. Basically did the same thing we did with the road, with the highway truss. We just lowered it down and got the transports out, and got ready to reset the new track section. Next slide. So here, the new track section is being raised into place, and then once it's all the way up, then we just use the transporters to crawl it back in and set it down with the gears. Next slide. So part of this with the being design and build, we had money left over that terminal was willing to use for the roadway demo. And what they did is they gave us a change order to basically demo everything from Broadway, from the old highway truss, and the old highway bridge, all the way back to the river. And so, I don't know, probably about half a mile of the old roadway got pulled out. But it wasn't just the old girders and the framing of it, it was all the bends and everything like that as well too. So it really opened the area up. But this was a challenge in and of itself. It was on-site and off-site, managing the demo contractor. They did a great job, but still, I mean, we work with demo guys that kind of get a little squirrely at times, and a lot of cutting, just a lot of, and again, around live tracks and make sure everything was coordinated with the railroad. But a really fun little part of the project. At the very end, to cap everything off, there was 2 sets of girders over Highway 55 and 44, whatever you want to call it, downtown, we had to remove. The heaviest piece was 800,000 pounds, and that's what Butterbridge there. They've got their 550 crane set up, and that's how we ended up taking the girders down. Next slide. So these are the girders over northbound 55 and 44. And how it was set up, we ended up having to have excavators, high rail excavators, up on the bridge, up on the railroad bridge while we did this, because it had to hold the inside girder as we cut the outside girder free. So night shift worked, they cut all the internal diaphragms free, got everything ready, and then day shift came in and removed the big girders, got everything down. But again, got the 550 hooked up to the outside girder, got it supported. The high rail excavators hooked up to the inside one just as holds. We cut the last little diaphragms free, or core beams, whatever you want to call them, free. And then the 550 took the big girder, reached over, grabbed the next inside girder, and then we're on the inside. Next slide. Here we are, this is on the southbound side. That looks like the last girder coming out. But again, kind of the same thing we had to do. Excavators are up on the rail.